thank you all for coming to the Purdue Engineering Distinguished Lecture Series. It is my pleasure as the Associate Dean for Faculty in the College of Engineering to welcome you to this. For those of you that have been to these events before, that's great. For those of you that haven't, and particularly for students who have this opportunity, we love to bring in people that can share with you some of their stories, share things about what's going on right now, and really what's making a difference across all sorts of fields of engineering. So today I'm pleased to welcome Dr. Robert Braun. Dr. Braun is the head of space exploration sector at Johns Hopkins Applied Physics Laboratory. He's responsible for all civil and national security space activities at APL, including strategy, finance, personnel, programs, everything that handles civil and spaceflight. He has over 1,300 team members that report to him through this operation, which he runs he has a big crew out there. He's previously served in executive roles at JPL, Director of Planetary Science, and NASA, and has served as a tenure faculty member at 3 universities, Georgia Institute of Technology, Colorado Boulder, and Caltech. So we're glad that he's come to a good one now. And what I love is that these things are recorded, and so I will always be on tape being flippant. I apologize. He's contributed to the formation, development, and operation of multiple spaceflight missions and is recognized authority on the development of entry, descent, and landing systems for advanced hypersonic technology. He received a BS in Aerospace Engineering from Penn State, a Master's in Astronautics from George Washington University, and a PhD in Aeronautics and Astronautics from Stanford. So with that, I'd like to welcome Dr. Braun to the stage.
Oh, wow. Move this out of the way. Oh, maybe this way. Do that. Okay? All right. Good afternoon. Can you hear me okay? Yep. Yeah, good. Good. Thank you for coming out. I hope you're getting course credit for this, or it's probably, yeah, I know how it works. But in any case, thank you for coming out. I am very excited to be here at Purdue. Just for the record, I never had an offer, so just since we're recording things, I might as well say that as well. Generally speaking, I'm someone who's done a lot of work in atmospheric entry, hypersonics, entry, descent, and landing. So how you land spacecraft on other planets. And I'm going to touch on that a little bit today, but I was kind of excited to put together a different talk than what I would normally do and talk about something that I've been bothered about my whole life, actually. And that's about autonomous systems that are now starting to make their way into deep space exploration, really in the last decade for the first time. It may sound silly to you because you see autonomous systems everywhere you go, here on the Earth, but it's taking us a while to get them into deep space. And, when I was a kid watching Star Wars, I imagined, autonomous systems would be there the day I started working at NASA. But that really wasn't the case. And so I want to kind of walk you through that and walk you through some of the changes that are occurring in our space program that you may not have even noticed, but they're happening before your very eyes. So my basic thesis is shown on this slide, which is, if you think about spaceflight, what's the phrase that pops into your mind maybe first? What's the first thing that you think of? Mars. Oh, Mars is good. Yeah, that's good. I was thinking like Houston, we have a problem, right? So when they said, Houston, we have a problem, they weren't actually on board ready to solve that problem. They phoned home. They phoned home to the hundreds and maybe even thousands of engineers in mission control who were going to work that problem for them. And that's how the early days of spaceflight went, right? We had a lot of expertise on the ground and we had some expertise in space, but we basically counted on the ground when there were problems. And so, the early days of spaceflight were built on this ground-in-the-loop operations, whether we were talking about going to the moon, or even for robotic systems that were going way out, into the solar system. We had mission control for those as well. We had expertise for those as well. And so in deep space operations, which is what I'm going to focus on in my talk today, this culture of counting on the ground has persisted for a long time. We think of our robots, our autonomous, our machine emissaries as being very advanced, and they are, but they haven't really been autonomous until recently. And in this past decade, you've started to see, I've started to notice, lots of autonomy in our systems for deep space exploration. And I'm going to walk you through some of those autonomy advances in the talk today, because I think it's a remarkable change. It's one that's long overdue, and it's going to really help us accelerate the pace of exploration and discovery in the coming years. Also, for those of you that might be graduate students or aspiring faculty, there are all kinds of new fields that need to be explored. If our robotic systems are going to be truly autonomous, the software that they run on becomes more and more important. How do we know? How do we trust that software? How do we know that it's going to actually do what we intend it to do? And so there are all kinds of methods that need to be developed for these autonomous systems in the coming decades. And I'll give you some examples of that. Before I jump into examples, though, let me make sure you understand what I'm talking about. So for as long as I can remember, and I'm talking about our robotic missions to Mars or to the planets, for as long as I can remember, those missions have been what I would call automated. They have automation. So we used to, like the very early rovers at Mars, the Sojourner rover, for instance, we would say, all right, today, drive 3 feet straight ahead. And the next day, it would have driven 3 feet straight ahead, and we would say, okay, today, turn to the right. And the next day, it would turn to the right, right? It executed those commands in an automated way. We weren't joysticking it from the Earth, for example. But it really wasn't self-directed, right? It was following our commands from ground control, from where the expertise was back at Earth. Now, by autonomy, what I mean is the ability of the system to achieve goals while operating independent of external control. This is a standard definition for autonomy, but it requires self-directedness and it requires some self-sufficiency. Think about, autonomous cars, for instance, here on the Earth. Requires the same thing. And in the last decade, what we're starting to see is these kinds of autonomous systems make their way into spaceflight. So instead, for instance, of a rover like the Sojourner rover being given the commands that I just went through, in this slide here, I'm showing the Curiosity rover, which is told to go to a waypoint, let's say way off in the distance, and how it gets to that waypoint is totally up to the rover. It has hazard avoidance capability. It has imaging capability. It has all the orbital images from above, and it plots its own course. Or it decides on its own to do science measurements at a particular location on the way. And so we've really advanced the sophistication of the Mars rovers, for example, over time, or the satellites here around the Earth over time. And that's allowing us to reap much more from each one of these investments. There's actually a really good report on this if you're interested in diving a little deeper. About 4 years ago, the Office of the Chief Technologist at NASA headquarters put out this report in the middle of the slide called Operation of Autonomous Space Missions. And it walks through all the functionality and the capabilities required to take something that was automated and turn it autonomous, right? Now, when would you like to do this? When do you think we might need to do this, right? Well, typically when the cadence of decision making is rapid, think about how long it takes to send a signal one way to Mars and have it come all the way back, many minutes, right? If our rover is driving towards a cliff, right, you want to make sure it has some autonomous capabilities to stop when it approaches that cliff, just as one example. When decisions are time critical, maybe the health of astronauts, think back to the Houston, we've got a problem example. How we might attack that challenge today would be very different than the way we would have attacked it in the 1960s. When decisions can be made better with the very large amount of data that is likely available in situ. So our systems at Mars today can send back so much data for example, that we don't even process it all in a very rapid time when we receive it on Earth. And so our systems could be processing that data themselves, right? They could be analyzing the data, making decisions on their own, and just sending back the data that's important for our scientific objectives. Given our limited bandwidth to do so, that's probably a better way to go. And so these are all reasons why you might imagine an autonomous system for deep spaceflight. Even here at the Earth, you see more and more of this capability. Now, I'm not talking about Skynet from Terminator fame, for example, but you think about the Starlink system and the autonomy that's on board there, right? We're talking about either communications or navigation or reconnaissance at the Earth now with large constellations of spacecraft where there used to be like a single spacecraft that did that work from, let's say, geosynchronous orbit. Now we have constellations of spacecraft in low Earth orbit that have to sync up, share data, decide which data to send down to the Earth at what time. And so autonomous systems is not just for spaceflight, it's not just a deep space thing. It's happening in Earth observing at a very fast pace as well. But what I want to focus on is deep space exploration because it'll be, a little more interesting. And maybe the best way to start is with this video. Maybe. There we go. From a few years ago when I was at JPL.
Propulsion. Go. EDL phase lead. Go.
We have deemed Perseverance ready to
during
execute entry,
COVID.
descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance
Safely on the surface of Mars, ready to begin seeking the sands of top flight.
So maybe you remember that. Maybe you were remember where you were in February of 2021. At least I hope so. I know exactly where I was. I always get choked up actually when I watch that video because even though it was 4 years ago now, that team of people and what they accomplished, in the midst of COVID. We launched in June of 2020. By the way, COVID had only been going on for 3 months at that time. There weren't shots in your arm. We had people having to go back and forth between California and Florida to pull that mission off. There were folks all over the country that worked on that mission. And what they accomplished together was remarkable in its own right, but as you saw in the video, the world kind of celebrated with us and it felt a little lighter, a little sunnier that day. I'm very proud of that team. But the reason I'm showing you that slide is not because of the accomplishment itself or how much I love working on that with that team. I'm showing you that, whoops, there we go, this way. Because I've worked my whole life on Mars landings, figuring out where these landers should go, making sure they get guided safely to the surface. And this was the first time I didn't know where we were going to land. I thought I knew where we were going to land because that was my job, actually. And that's something I thought pretty good at. But for Perseverance, nobody in mission control knew where we were going to land. And that's because we went from automated entry, descent, and landing systems to Perseverance during entry, descent, and landing deciding on its own. It had enough smarts, it had enough sensors, it had enough capability to autonomously pick a safe zone. The closest safe zone that the wind blew it to while it was on its parachute. And it had propulsion on board to maneuver to that safe zone. And so none of us knew exactly what the wind would be like on Mars that day. And so we didn't know precisely where it would land. And so we could send it to a region of Mars that we would have never gone to before because it was a dangerous place to try to land. And if we had said land right here and we had missed, we could have had failure. But because we had this autonomous capability on board, we were willing to take that risk and let the system figure it out. Let me show you that in a little more detail on this slide. These are hazard maps of the local terrain where Perseverance came down. You can see on the scale on the right that red is what we would call death, and it gets better and better from there. You can see in the image on the left that we landed, Perseverance on its own landed exactly where it should have landed, in a big blue sea, where there's nice terrain, nice soft landing spot, not a lot of rocks, not a lot of slopes. You see the dot on the left-hand side. If you go up and left to the diagonal, you see a big region that's blue. That's where all of us were betting that we were going to land. We called that the runway because it was nice and smooth. It was almost like it was paved, ready for us. But you see where we landed? We landed nowhere near the runway because the winds took us in a different direction. And look at all that dangerous terrain around where we landed in that image on the left. So this system took us to scientifically interesting region of Mars and landed us safely in a way that we on the ground really couldn't have done. Isn't that what autonomous systems are supposed to do? Right? So it's a remarkable example, for me at least. This is in my own field. We never would have attempted this on Mars Pathfinder, on Spirit and Opportunity. We never would have even done this on Curiosity. We just didn't have the capability on board in the time that we had on Perseverance. And of course, Perseverance took along a companion, Ingenuity, the first Mars helicopter. And Ingenuity was designed to be a tech demo. All it really had to do was go vertically up about 5 feet and come back down. The first flight on another planet, a Wright brothers moment. It did that, but then it turned into a scout for Perseverance. It had its own hazard capability that we didn't even send it until after it was on Mars. We coded it up after Ingenuity was on Mars, sent it through the Deep Space Network. Ingenuity adopted that software as part of its baseline, and all of a sudden it was smart. And it could find hazards, and it could fly over terrain that we would never have sent it to. And as such, it could scout ahead of Perseverance and send back imagery and other data to help us determine where Perseverance should go next to acquire the best sample, because we were acquiring these samples to one day bring back to the Earth. And we didn't even add that capability until about 30 flights in on the Ingenuity helicopter. So that's also, I think, part of this journey. I then want to move to this example at the Applied Physics Lab. DART. Anybody here at DART? Yeah. So we took a perfectly good spacecraft and we smashed it into an asteroid, destroying it, right? But we did so in the name of planetary defense, so that if there was ever an asteroid like that coming our way, we would have a validated technique to deflect that asteroid away from the Earth. And we actually purposely impacted an Earth-crossing asteroid, but not one that was going to be a danger to the Earth. This is kind of an overview of the DART mission. It was launched in 2021, and it was targeting a binary asteroid system, meaning a system with a smaller asteroid, Dimorphos, that was orbiting a larger asteroid, Didymos. We could see Didymos from the Earth, and because of light curves, as the smaller asteroid passed in front of the Earth as it went around, we knew there was a smaller asteroid there. But we knew almost nothing about Dimorphos at the time that we launched the DART spacecraft. I should also point out the Licia cube, which was supplied by the Italians, that kind of flew behind DART. Where's my faculty friend? Oh, there you are. Licia cube, yeah. That flew kind of in like a wingman, if you will, and took images of DART as it headed towards its encounter with Dimorphos. Now, this is a great image, but what it doesn't tell you is that because we knew so little about Dimorphos, that we let the DART spacecraft be fully autonomous in the final 4 hours. So it could target, orient itself, use its own propulsion system, the whole shebang, all on its own in the last 4 hours to make sure that we had a proper impact and that we didn't miss the target, right? And that's because, as I was saying, we had some knowledge of the primary asteroid. We had, you can see it there in some telescope images. We had a radar model of its rough shape. But what did we know about Dimorphos, which is actually the target, right, that you're trying to hit? We didn't know much at all. And in fact, what we knew is there are all kinds of asteroids out there. If we assume it's a spherical asteroid and it's a dog bone shape, we could miss it entirely. In our simulations, by the way, one day I asked them to program in a donut. And so the team thought they were like going right down the center, right towards the target, and they flew right through the donut hole. They had to figure out what had happened. Thankfully, it wasn't a donut, right, in reality, but it was a fun simulation. So we knew almost nothing about Dimorphos, which is why we had to invent, as part of the DART mission, a smart navigation system. Basically a set of algorithms that were on board that would allow the spacecraft to have some self-autonomy, to self-inform itself, to control its orientation, to control its thrusters, to go from targeting the main body asteroid that we could see from the Earth and navigate to tracking the orbiting asteroid that was coming around the limb, right, which we couldn't see, once again, from the Earth. We ran all kinds of simulations to prove that we could do this. And actually, after we launched, we used the moons of Jupiter to test out our capabilities. As they came around the limb of Jupiter, we tried to move our system from tracking Jupiter to tracking the Jovian moons as we were headed towards this asteroid, just to prove out our capabilities. And by improving the software all along, we greatly improved the probability that we were going to have success. At the time of launch, it was pretty 50-50 if we thought we could actually impact the right asteroid. And by the time we got there, our team was confident with greater than 80% chance, they thought, of impacting the right asteroid. And of course, that's what happened. What I'm going to show you on the next screen is what it looks like as we were approaching that asteroid. But to give you a sense of it, if you look very carefully in the image on the left, this is from 90,000 kilometers away, 4 hours before impact. This is what the spacecraft could see. It could see both asteroids, actually, if you look real carefully. But as we got closer, it could really detect the smaller asteroid because it was coming around the limb at that time. And so even though we could have seen it at 4 hours out, we couldn't because of its position. So 73 minutes out, 27,000 kilometers to go was our first detection of our target, Dimorphos. You can see what it looked like about 2.5 minutes out and just a few seconds out. And I've got an animation of that'll walk you through this in a little more detail. So these are images from our onboard camera. It's sped up a little bit. This is the last 5.5 minutes. You can see the main body asteroid in the foreground and the one we were aiming for in the distance. The reason it's jittery is either attitude control or propulsion system firings that are all done autonomously. And you can see that we zeroed in. This is at 10 times speed, except for now it's going to be real time. Boom. So, I've been in a lot of missions, right? I've been in mission control quite a bit. I've never been so excited to have loss of signal. Right? Normally, you're panicked. Loss of signal, something's wrong, right? But this was the last image we got, and of course, in mission control at APL, we erupted in success. But it's funny, like we're all standing here, we're in mission control. This is an image from that room. You got the headsets on, you got the consoles. But in those last 4 hours, what were we doing? We were watching. Just like anybody who was watching on YouTube. Because it was an autonomous system at that point. Anyway, it was a fantastic day, a fantastic event. We used ground-based and space-based telescopes to watch the event. This is an image from Licia Cube that I mentioned earlier, Wingman. Here's an image from a telescope in South Africa showing that impact event. Pretty significant event. Even like 12 days later, the asteroid was still bleeding material into the trail here as it was headed on its course forward. This is from the Hubble Space Telescope. The purpose of the experiment, once again, was a kinetic deflection. So how much would we change the orbit of the small asteroid around the big asteroid? And so there were radar observations made all throughout October. And those radar observations are shown here. You can see what's shown is the orbit of Dimorphos and where we expected that system to be had we missed, had the system been occurring naturally versus where it was. So we changed the period of that orbit by a good bit. And the impact event was about 5 times more impactful because of the ejected material than we had expected. So that's very useful information for when you're thinking about an Earth asteroid, coming towards the Earth, especially if Bruce Willis might not be available, right? Anyway, a fully autonomous system. I'll give you another example. A lot of words on this slide. Don't worry about all the words. But on Christmas Eve of this past year, the Parker Solar Probe, another APL mission, flew by the sun, closer to the sun than any system has ever been. You can hear what the environment, basically, that it flew through, the dust, the solar wind particles, as it was flying through the sun. Now, it's on the far side of the sun while this is occurring. So from the Earth, there's nothing that we can do. We're being blocked by the sun. So Parker had to be fully autonomous for months at a time to accomplish this. And because it was so close to the sun, if its orientation was off by more than half a degree in attitude, it would burn up. Right? So it had to hold its attitude control. It had to fly its pre-planned trajectory just so. And the autonomous system that was operating for months at a time was responsible for Parker as it flew closer to the sun by a factor of 6 or 7 than any other human-made object. Right? So we're really counting on autonomy. Right? We're counting on it to land spacecraft at Mars. We're counting on it to deflect asteroids. We're counting on it to learn about our own sun. And coming up in 2028, when we send the Dragonfly mission to Titan, we'll be counting on an autonomous system as well. Dragonfly is an 8-bladed quadcopter drone about the size of a car. It's nuclear powered, launching to Titan in 2028. Of course, Titan is a moon of Saturn, very far away. The one-way signal time is quite long. So the system has to be, and we're not always in view of Titan as the planets go around the sun, and the moon of Titan goes around Saturn, right? It's a complicated objective. And Dragonfly is going to land and do science at dozens of landing spots over let's say roughly a 300-mile trek across Titan over 3.3 years. Right? So we can't be controlling that from the Earth. It's got to go to the next place on its own. It's got to do its science on its own. We'll tell it things like, hey, you did a great job yesterday. Take a break today and just recharge, right? Or we'll tell it things like that. But the day-to-day events that it's controlling on Titan, it has to do on its own. This is a very interesting planetary science mission that we're doing actually with Lockheed Martin. And many others around the nation, launching in 2028. This is the biggest space program at APL right now. And then if you look out a little further in the future and you think about what's planned, what does NASA have planned? We have Europa Clipper going to Europa right now, but where people really want to go is to the surface of Europa. They want to explore the surface of that ice-encrusted world. They want to go to Enceladus, which is also an ocean world that's spewing water out into the solar system. There's no way we go to Europa, there's no way we go to Enceladus without autonomy, right? These landers are going to be even more autonomous than what I'm talking about today. Because of the distance, because of the type of operations that they're going to want to do in these locations, very sophisticated operations that people on the ground are just going to receive the data after many years planning out those operations and developing that software. Once that system launches, it's going to be on its own. It's going to be fully autonomous. And another example that I'll mention, the last one, is interstellar probe. Interstellar probe is a priority of the heliophysics community, so the community of scientists that study our sun and all the stars, right? All the stars you see are suns. There's actually a group of them that are working on sending a spacecraft built here on the Earth to another star, right? Wouldn't that be something? Well, it does, regardless of how much energy we give this system, when it goes off to another star, the stars are a long way off. And so it's going to take many decades for interstellar probe to get to that star. And so the people that designed it, their grandkids might be receiving the data, right? And so, this system not only has to be autonomous because of the distance and how difficult it'll be to communicate with the interstellar probe, that it's going to have to process a lot of the data that it observes in this new star system. Let's say it comes up on planets in this star system, right? You're going to want this probe to be able to analyze those planets on its own, not sit there and wait for us to tell it what to do. The one-way light time is also prohibitive. And in this case, we're talking about generations that will have gone by from the time we designed and launched this system to the time that it's actually getting data around this star system. So there's no way we do this either without autonomous systems. So anyway, what I hope that you've gotten out of this today, first of all, thank you. What I'm hoping that you've got out of this today is a couple things. One is Star Wars is coming. Star Trek is coming also. I don't want to get into a fight between the Star Wars people and the Star Trek people, by the way. They're both super cool. But really, going back to the beginning of the space age, because of the risks involved, even in sending a robotic system, let's say to the moon or to Mars, you didn't want that system to fail. And so you made, given the computer technology at the time, right, you made those systems very dependent on the Earth. All the smarts was at the Earth. And so, you would phone home whenever there were problems. And while that culture has pervaded the space community for decades longer than, computer technology has been around and even in your smartphone, right? The space community's come around, and you're starting to see in the last decade, you're starting to see use of autonomous systems to enable deep space missions that we could only dream about before. Missions like Perseverance that are far more capable than, let's say, the Sojourner rover from the 90s. Or missions like Dragonfly that, a nuclear powered card size flying machine on Titan looking for the origin of life. I mean, who doesn't think that's cool, right? And there's no way we do these things, DART, interstellar probe, without autonomous systems. So I'm really excited that the future I wanted to see when I was a kid is finally here. And I thank you for listening to this talk and walking down memory lane with me. Thank you very much. We have time for some questions? Yeah.
Just going to say, we have time for some questions. Please wait to ask the question until somebody brings a mic to you. So we'll have two people running, and I'll try to point to who we go with. So let's start over there, and then I'll
Yeah.
go. We'll do the standing one. Yeah.
Hi. Over here.
Hi.
Thanks so much. This was a great talk. What do you think has enabled sort of these improvements in autonomy over the past, whatever, like a few decades?
Yeah, so a couple of things. Clearly, compute technology, think about your smartphone. When I was in college, I didn't have one, right? And then, I got one eventually when I was working, and I had the flip phone, and it wasn't really a smartphone, right? You have more power, you have more computing power in your smartphone than we had on the space shuttle, just as an example. So compute technologies come a long way. Autonomous systems here at the Earth have come a long way. So all the software advances, trust and verification, validation approaches that we use for robotic systems operating around humans, that has certainly enabled us to do better testing of robotic systems. And then I just think the goals of the missions have gotten more advanced, right? So if you think about deep space exploration, the 70s and 80s were about flybys. We flew by this because that's all we could do, right? We flew by the planets, took a couple images and moved on, right? And then there was about orbiters, right? And then eventually landers. And now we're talking about true autonomous systems. I think it's a natural evolution in our thinking about these robotic missions, the goals that we set for them, and also the engineering that enables them.
Hi. Thank you for the talk. So I guess the motivation has largely from the distance and the time delay of the deep space exploration nature of it. So could you share your thoughts on the near Earth regime, whether it's more important or like more or less, or equally important?
Yeah, no, I think what you're seeing here at the Earth is more advances in autonomous space systems as well, for different reasons. It's not because of the one-way light time, right? But it's because of the disaggregated nature of our space systems, the use of constellations to do what used to be, if you had a certain measurement objective on the Earth, you might have spent 10 years building the perfect spacecraft to go after that measurement objective, loft it up into geosynchronous orbit where it could sit and stare at the Earth and take those objectives. But that system might cost you $5 billion, just to make up a number. Today, you go after that objective with a small spacecraft, and you launch like 10 of them, and then you launch 10 more, and then 100 more, and then 1,000, and you do it with low Earth orbit. And so if you're approaching those same measurement objectives from low Earth orbit, those systems have to talk to each other. You have to be able to decide which one do I want to talk to at which time from the ground to do a particular objective. You can control all of that from mission control, but it's pretty intensive. And so if you can make that autonomous, then you don't have as many people in mission control. You don't have to pay for those people. You can have a lot more software developers, if you will, than mission control types. And I think that's the way of the future. I think small spacecraft is a revolution in its own right, and that's enabling autonomous systems, in Earth spaceflight.
Dr. Braun, thank you so much for your talk. It was so fascinating. Like you said, like watching Star Wars, it's like what you show with asteroids. It was crazy.
Yeah,
and I want to talk about the program that is launching to another star. How do you think those aircrafts are going to be powered? Because they're going to have to sustain for probably like thousands of years. I don't know.
Yeah. Yeah. So I should have mentioned it. So Dragonfly, for example, is powered by what's called an RTG, a radioisotope thermal generator. So it basically produces electricity through the decay of radioactive material, and it operates on only 100 watts of power. So I know I'm not directly answering your question. I'll get there in a second. But so Dragonfly basically has days where it sits there and charges, and then it has days where it flies, and it has days where it does science, and that's all power limited. So Interstellar Probe is going even farther, right? And so if you're going to Saturn, you can make arguments that maybe we can use solar cell technology, but they're not that compelling. Jupiter, you can certainly do with solar. But if you're going to Saturn or beyond, you're going to end up using like an RTG or many years from now, we'll use fission, nuclear reactors for power. And so Interstellar Probe is talking about several RTGs that it would take to power the system. And they last, as long as, it's a radioactive decay. So they last, they're at a decaying rate, they last for many decades. Yeah, many decades. But you have to size it for the lower power that occurs over time.
We'll give somebody that's in the very back, all the way back there. Somebody that's behind the pathway, we'll get them next.
Yeah, by the way, this is like the coolest venue ever. I mean, like with all this stuff. Very, very impressive.
Thank you for the talk. I have two questions, primarily just on the basis of autonomy. I understand the DoD, namely DARPA, are looking at autonomous systems for programs like collaborative combat aircraft for like loyal wingman purposes.
Yeah.
How much in conjunction, if at all, is NASA, JPL, these kind of spacefaring agencies collaborating with the defense agencies in that regard? Is it working in parallel, or is it a completely separate initiative? And then the second question, much more technically, regarding the DART intercept mission, do you know off the top of your head like the delta V imparted, or like how did they like specifically hit the asteroid? Was it like in the same direction it was already moving, or like just specifics there?
Yeah, I can talk a little bit about that. And some of your faculty, actually, I think, Kathy, you were on that mission. So Kathy Howell here could talk about it in great detail. But let me try to get at part of your question. So yeah, there's a lot of synergy between defense and civilian space, NASA space. JPL tended to focus, because JPL is NASA's agency, they tend to focus primarily on NASA work, not completely, but primarily. At APL, where I am now, the Applied Physics Lab, we're about half and half between NASA work, NASA and NOAA work on the civilian side, and all kinds of Space Force, defense, DARPA work for the DoD. In fact, many of the engineers at APL will be working, Monday, Tuesday, Wednesday on NASA stuff, and Thursday, Friday on a Space Force program. They're doing that at the same time. There's a lot of sharing that occurs. So, for instance, in DART, the algorithms that actually enabled us to basically have a bullet hitting a bullet came from the Missile Defense Agency. They came from work that APL had done for the Missile Defense Agency. On Parker Solar Probe, our heat shield that kept us safe when we were near the sun, that's the same kind of materials that we use in hypersonic applications, for defense. So there's a lot of synergy in technologies. There's also a lot of synergy in people's brains. And so at APL, I find that helps. Sometimes we'll work on a NASA problem and it benefits the DoD, and sometimes we're working on a DoD problem and it benefits NASA. So you find that in industry as well, at companies like Lockheed Martin or others. In terms of your question about DART, it was planned as a head-on collision. So as the moonlet was coming around, we set up to have maximum velocity change, maximum energy change by aligning the velocity vectors as close as possible. We wanted to hit that asteroid as close to the centroid as possible. We were really close on both the centroid and on the velocity angle. Do you remember the exact velocity change? The period changed by about 37 minutes, and we were expecting, the requirement was that we had to change the orbital period by about 6 minutes. So we greatly exceeded, because of the mass of material that was ejected from that impact event, which also is momentum exchange, right? Because of that, we greatly exceeded the requirements for the mission. Okay?
So obviously we don't have hyperspace yet. And there's always kind of been a proportion of, if you're sending something into deep space like interstellar, the trade-off of how many decades is it going to take to get out there, and in that time, could we have developed something that's fast enough to lap ourselves?
Yeah.
So is the people on the project that are working on interstellar right now, going towards the future, are you guys confident that you're hitting a point where, you're not going to lap yourselves in the decades that Interstellar is going to be out there for deep space and other.
You know, I'd be fine if some future generation lapped us. I think that'd be great, but it doesn't mean we shouldn't go now.
Right.
Right. So, so New Horizons, which is a APL mission that flew by Pluto and now is in the Kuiper Belt, is going faster than the Voyagers. So it will eventually pass Voyager 1 and be the farthest spacecraft from the Earth. It doesn't take anything away from Voyager 1, which was an amazing mission, right? There's also a lot of stars. So, you know, even if Interstellar Probe is using today's technology and goes at a certain rate, and maybe it takes us 50 years to get there, let's say, if 20 years into it, we have a new system with new technology that can go way faster and potentially lap us, maybe we go to a different star with that system, and then we have both. You know, there's probably, I mean, there's as many worlds around these stars on average as there probably are in our solar system. There's an awful lot of stars in the night sky that one might want to explore. They're probably all different in their own ways. So I'd like to see, you know, dozens of interstellar probes. The first one, and then as technology evolves, they get better and better. Much like the Mars rovers. You know, I worked on the little Sojourner rover, was about the size of my baby daughter. She was born around the time that we launched. And, you know, I could hold either one in my arms. That certainly was not true of Curiosity and Perseverance, which are car-sized rovers and nuclear-powered, right? Very different technologies, very different capabilities. So I hope that we continue to evolve and innovate with technology over time.
Thank you.
Okay, we have one more question before we break and the chair people come. So why don't we do it? But that doesn't mean you should leave, because you should stay for the panel discussion that's coming up right afterwards.
All right. Thank you for the talk again. I'm going to be spreading all these fun facts sprinkled throughout all my conversations for the next 2 weeks. And so I had a quick question. One was, given this power limitation that these long-term missions have, the ones that take 50 or 100 or thousands of years, what is the plausibility of maybe some kind of AI or neural network on them functioning or like running the autonomy?
Yeah. Well, I think you're going to see that, right? So today's autonomous systems are not what we would call AI. They're not what we would even call machine learning kind of systems. But, you know, 10 years from now, sure, absolutely. If we want our autonomous systems to have more and more capability, and we want them to actually process the data, you know, with edge computing, like advanced computing out there on the edge, right, where they are. We want them to process that data and to only send back the really interesting stuff, then they're going to have onboard intelligence to do that. And whether that's AI, what we call AI today, or whether that's AI generation 3 that hasn't even been invented yet, I imagine that will continue to evolve. Yeah.
Okay.
Thank you.
So I'm going to interrupt here and say on behalf, try to do this. So on behalf of the College of Engineering, and I'm going to walk this way because I'm going to get photoed.
I'm going over here.
Yeah, we're going over here. So on behalf of the College of Engineering and in honor of our 150th anniversary, we're happy to present Dr. Braun for recognition and appreciating contributions to our distinguished engineering lecture series.
Thank you.
Thank you very much.
Thank you very much. Thank you.